In the last class we saw different versions of spectral theorem, resolution of identity, continuous functional calculus, L infinity functional calculus and the multiplication operator form. Okay. So, now we will prove that they are all equivalent. Okay. Starting from one form we can get other ones. So, we prove that all of them are equivalent, and remember that we have already proved at least the multiplication form for normal operators and also the projection valued or the continuous functional calculus we have proved for normal operators. So, we can get all the other forms by because of this equivalence. Okay. So, let us start. So, first one implies 2. Okay. So, that is resolution of identity implies continuous functional calculus, right. This is something which we have more or less done. Okay. So, resolution of identity implies the continuous functional calculus. Okay. So, proof of this, since this is what we did after defining the resolution of identity, right. So, once we have the resolution of identity, we know how to define an operator for each continuous function, right. So, let us try to do that. So, if you have E sub t, right, E sub t is your resolution of identity, that is given to you, right, resolution of identity. Okay. We know how to define, phi, right. In our notation it was phi of g, right. Remember we defined phi n g, which was a Riemann sum, and then we proved that it converges to some operator which we denoted by phi of g or the integral, right, or the integral of g against dt. So, to define integral of g det, and the convergence were actually in the operator norm, right, as long as g was a continuous function, right, for g continuous in let us say minus a to a norm a, right, because the resolution of identity is supported there, right. So, if resolution of identity was supported in minus r to r, we defined an operator for all continuous functions there, and that is what was the continuous functional calculus, right, with phi of the identity function, right. So, identity I d x equal to, so I d x equal to x was equal to t d e t equal to the given operator a, right. So, resolution of identity implying continuous functional calculus is more or less trivial. Okay. And so, let us look at second one. So, maybe I should go to the next page. 2. Okay. Continuous functional calculus, implies the multiplication form. Let us see why that is true. So, this requires some work, but this is a proof which you have already seen. Okay. So, we construct measures using continuous functions and representation theorem, and we transfer our operators to the L2 space which we have constructed, and we get multiplication by the Gelfand transform and so on, right. That is precisely what we are doing. So, given continuous functional calculus, so we denote it by phi, right. That means, we have phi from continuous functions in minus a to a, minus norm a to norm a, to bounded operators on the Hilbert space, which takes identity to. So, phi of identity equals the given operator a, and it is an algebra homomorphism and what not, right. So, we have phi, right. I will not write phi sub a, it should be clear because there is only one such homomorphism in place now. Let us assume that V in H is cyclic for A. Okay. That is the simplest case, right. So, what does it mean to say it is cyclic? That is you keep hitting V with A. So, you have V, you have AV, you have A square V, etc., and you take the span closure of that. That should be all of your Hilbert space. That is, you look at A to the k V, right, k going from 0, 1, 2, 3, etc., and then you take the span of these guys, those have finite linear combination of things from there, and you take the closure, that should be equal to the Hilbert space. Okay. Now, define, now you do exactly what we have done before. So, this is a proof which you already know. The map G going to G of A, right. So, G of A, so that is a notation we are going to use. So, phi of G is going to be an operator, right. So, that we will denote it by G of A, right. If G is the polynomial x going to x square, we are going to get a square, right. So, that is why that notation is consistent. So, G going to G of A acting on V, inner product with V, right. So, this is how we define the measure mu V V, right. If you remember mu sub V V, this is precisely what we did, right. So, where is G? G is in G is a continuous function on minus norm A to norm A, right, and G of A is of course a bounded operator, right. But when I take the inner product, these are going to be complex numbers, and well, I know it is a linear map because G going to G of A, that is a star homomorphism, it is linear map. So, it is linear, and whatever from functional calculus we also get that this is continuous, right. So, since modulus of G of A V V, right. So, I want to say this is a continuous linear functional on the space of continuous functions on minus norm A to norm A, right. So, this is less than or equal to norm of G of A times norm V square, but norm of G of A is less than or equal to the L infinity norm of, right, the supremum norm of G. Okay. Remember, we may not have equality even for continuous functional calculus because we are not specific, we are not restricting everything to the spectrum, right. We are looking at the interval minus norm A to norm A, norm V square. Okay. So, because of this quantity coming here, we see that it is a continuous linear functional from continuous functions on minus norm A to the complex numbers. So, by Rees representation theorem, there is a unique measure, right. So, by Rees representation theorem, there exists a unique, in fact regular and so on, you can put in whatever regular measure, which will say mu, but it depends on V, right. So, we will just to be consistent with the earlier notations we had used, it is mu V V, right. So, unique regular measure mu V V such that, so I may skip the subscript V if it is not necessary, such that G A V inner product with V is equal to integral, well integral is actually on the spectrum, but in our case we should actually write minus norm A to norm A. Okay. So, G d mu V V, okay, that measure. Now, well, we have to prove that this measure is positive, and we transfer the operator A to the other side, we see that it is multiplication operator, right, that is what we want to show. Okay. So, let us see if G is positive. So, how do we show that the measure is positive? We look at this, if G is positive, I want to say this integral is positive, and so the measure will be positive, right. So, if g is greater than or equal to 0, write g equal to h square, where h is greater than or equal to 0 and h is also a continuous function, right. The square root will be a continuous function if I have a positive function, right. So, that is all is there, and note that g is positive. So, g is positive, h is positive. So, the corresponding operators are also positive, right, in particular self adjoint. So, I can write, so note that h of a is positive, and so h of a star is equal to h of a. So, it is in particular it is a self adjoint operator. So, g of a I can write as h square a, right, g is h square is h a into h a, but h a is also h star, right. So, it is h star a into h a. Okay. So, now we know how to prove that the measure is positive, hence integral over g. So, I started with a positive function g, right. So, integral over g d mu v v equal to g a acting on v inner product with v, right, but g a is h a star v inner sorry, there is one more h a there, h a v inner product with v. You have seen this before, h a star goes to the other side as h j, and this is simply h of a v norm square. So, this is positive. So, for every g positive, right, I know that this integral is positive. Okay. So, hence the measure is positive, right. So, hence mu v v is a positive measure. Well, it is a positive finite measure. Why is it finite? Well, you take g equal to 1, because it is a positive measure, it is enough to look at the total measure, right. So, put g equal to 1, you will see that well, if you put g equal to 1, you are going to get identity operator on the other side. So, it is just norm v square, right. So, you will see that it is a positive finite measure. So, the finiteness comes from take g equal to 1, and you will see that the total measure of this, the norm, is equal to norm v square, right. So, that much actually comes from the fact that it is positive. So, now we can define the map a to the n v goes to x to the n. Okay. So, from where to where? A to the n is in the cyclic subspace you are generating, that is a Hilbert's that is a vector in the Hilbert space, right, and I am sending it to x to the n. What is x to the n? X to the n is the the function x going to x to the n. Okay. So, on this side I have, this is a vector on the Hilbert space, this is the function x going to x to the n in minus norm a to norm a, right, that interval. On that interval you look at the function x going to x to the n, right. Since a to the n v inner product with a to the m v, okay, this is equal to a to the n plus m. Well, why? Because a is self adjoint. So, a to the m coming to the left hand side would be a to the m star, but that is a to the m. So, I will have a to the n plus m acting on v inner product with v, right. This I know is integral, well, by the continuous functional calculus and so on. So, let us see what is the, where is that. Okay. So, here if you look at this, whenever I have g of a, I have the function g coming here, right. So, the function here, so I am looking at a to the n plus m, that corresponds to the function x going to x to the n plus m, right. So, this is x to the n plus m d mu v v, right. So, that is how it will look like. which is, so that is, this is by definition, right, by definition, okay, which is equal to, well, what is this? This is the inner product of x to the n with inner product of x to the m in L2 of mu v v, right. So, when I say x to the n, that is the function x going to x to the n and the function x going to x to the m, right. The inner product is simply integral of x n and x m, right. So, that is because there is no bar, there is no complex conjugate there, because everything is happening on the real line. So, you will have x to the n plus m, right. Look at this again, the map is a to the n v going to x to the n, right. So, a to the n is going to x to the n, a to the m v will go to x to the m, right. So, this preserves the inner product, right. Hence, the map a to the n v going to x to the n preserves the inner product on the span of a to the k v, k equal to 0, 1, 2 and so on. 2, so, when on it preserves the inner product on this span, meaning the span here goes to the span of x to the n's, right. So, span of x to the k equal to 0, 1, 2 etcetera. This is just polynomials in or defined on minus norm a to norm a. But these are dense, right. So, on the left hand side I have the cyclic subspace generated by V, right. Once I take the closure, I will get the whole H, because V is assumed to be cyclic. On the right hand side I have all polynomials in minus norm A to norm A. So, if I take the closure, I am going to get the class of continuous functions. Okay. So, it follows that. So, now I will leave it to you. So, polynomials are dense on L2 there, it follows that. So, and we have a map which preserves the inner product on this dense subspaces on both sides, and so it will extend to a unitary map, right. So, hence it follows that the map u of a to the n v equal to x to the n extends to a unitary map. Unitary map, well, the polynomials are dense in L2 of minus norm A to norm A. Okay. So, that is something you should keep in mind, because in supremum norm you will get all continuous functions and then continuous functions are dense, right. But the norm here is the L2 norm. So, if I take a continuous function, I have polynomials converging to it uniformly. In particular, polynomials will converge to that continuous function in L2, because we are on a finite measure space, right. And once we get all continuous functions, if you take the closure with respect to the L2 norm, you will get the whole L2 norm. So, polynomials are dense in L2 of minus norm A with respect to this measure mu, right, the mu v v and so on. So, it follows that the map u, which takes a to the n v to x to the n, extends to a unitary map from H, the Hilbert space, to L2 of minus norm A to norm A, the interval, with respect to the measure mu, right. So, mu, let us say v v, right, that was the notation, or just mu. And check that. So, this you can check now, check that u a u inverse equal to multiplication by x, multiplication by x. Okay. That is easy to see, because a to the n is what is a to the n v goes to x to the n, right. So, if I apply a to one side, I am going to get a to the n plus 1, on the other side I will get x to the n plus 1, which is x multiplied by x to the n, right. So, the operator is multiplication by x on all monomials and so for all polynomials and so for the whole space, right, because of denseness. So, under this unitary the A will go to multiplication by x. Okay. So, now comes the non uniqueness part. See, this measure is unique. So, when you have the measure here is coming from the Riesz representation theorem, and so that is unique, but that is under the assumption that the vector V is a cyclic vector. That means, A to the n V spans a dense subspace, right. In the general case, that need not happen. So, what we do is we start with one vector, look at the cyclic subspace generated by that vector and then go ahead, right. So, that is where the non uniqueness part comes in. Okay. So, in the general case, okay. So, what do? We obtain a maximal. So, here the Hilbert space is separable. So, you will get a countable collection. Okay. So, maximal set of orthogonal vectors Vi. So, now I is going to be 1 to infinity. Okay. If the Hilbert space is infinite dimensional, then you will get infinitely many orthogonal vectors or finitely many also, we do not know, such that each of them gives me a cyclic subspace, right. So, Vi, I look at V1, I hit it with powers of A, look at the span closure, that is one subspace of the Hilbert space, and that is left invariant under A, and its orthogonal complement is also left invariant under A, and we can continue. Okay. So, this is a proof we have already seen. So, let me quickly recall that. So, maximal such that if, so let us denote that by Hi, the cyclic subspace generated by Vi. So, Hi equal to span A to the k Vi, right. So, I fix an I look at powers of A acting on that particular vector Vi, k equal to 0, 1, 2 etc., and take the span closure of this, right. So, that is my Hi, okay. That is the cyclic subspace generated by Vi. So, cyclic subspace generated by Vi, right. So, if Hi is such that, then H is the direct sum of Hi. So, each Hi is a cyclic subspace, right. Notice that what is important is that A leaves all of them invariant. Okay. So, notice that A of Hi is contained in Hi and A of Hi complement is contained in Hi complement. In other words, each Hi is an reducing subspace for A. So, the way A acts on H would be that it will act on the components, okay, on each Hi, but on each Hi I can realize A as multiplication by x, right. So, by the previous case, A restricted to Hi can be realized as multiplication by x on L2 of minus minus norm A comma some measure mu I, right. So, what is this measure mu I? That is, in our notation it is mu Vi, right. That is the cyclic ith cyclic vector, and you take the corresponding linear function and construct the measure, right. So, on that subspace we can realize our operator as multiplication by x. Okay. So, A is going to be unitarily equivalent to, so first of all the Hilbert space, after that we can write. So, H is equal to direct sum Hi, and so that is going to be unitarily equivalent or equivalent to the direct sum of these L2 spaces. So, L2 of mu I, right, everything on minus norm A to norm A, I equal to 1 to infinity, and the operator A is going to be unitarily equivalent to multiplication by x on each of them, right. So, it is let us say m acting on direct sum f j, j equal to 1 to infinity is going to be direct sum x j f x f j, right, j equal to 1 to, sorry, there is no x j, x. On each component you multiply by h, right. In the cyclic case there is only one such component. So, this is a proof we have seen before, and it is just the repetition of that. But we started with continuous functional calculus and we have the multiplication form. Okay. So, the next one is 3. Multiplication operator form implies the L infinity functional calculus, that is actually more or less trivial. So, multiplication operator form implies L infinity functional calculus, L infinity functional calculus. Well, how does that follow? So, multiplication operator form means what? A can be realized as multiplication operator, right. So, I have the Hilbert space H to be. So, let me rewrite that once more. The Hilbert space can be written as direct sum of L2 of let us say minus norm A to norm A. In fact, one can restrict it to the spectrum, but we will not bother about it, and I have these mu i's. Mu i's are finite measures, remember that, I equal to 1 to infinity, right, something like this, and A is, so A acting on, so after taking the unitary copy, right. So, I will just write A instead of u A u inverse and so on, direct sum f I equal to 1 to infinity. So, direct sum f I equal to 1 to infinity is an element on the Hilbert in the Hilbert space, and it is supposed to give me a function x, supposed to give me a function, and I evaluate it at the point x. This is simply direct sum I equal to 1 to infinity x times f I x, right. Now, how do you develop L infinity functional calculus if you have that? Well, that is more or less trivial, because if you look at A, what is A square? A square is multiplication by x square, A cube will be multiplication by A cube. Polynomial, if I take in A, it is going to be that particular polynomial in x multiplied by whatever that f i's are, right. So, whatever polynomial in A you take, that is the multiplication by the corresponding polynomial. So, what is the L infinity functional calculus? You simply have to define, for any bounded function, you simply define the bound operator which is multiplication by that bounded function, that is all is there, right. So, if phi is bounded, then, so phi is bounded meaning phi is bounded on this set, right, it is defined on minus norm A to norm A. Okay. So, if phi is bounded, then define phi of A to be equal to multiplication by phi of x, right. That is the L infinity functional calculus, that respects all the properties you want, right. Phi bar will go to multiplication by phi bar, but then that is the adjoint of phi of A and so on, right. So, it will be a star homomorphism from functions which are bounded to operators on the Hilbert space H, right, which is what we want, and all the properties. So, I am not completing the proof, because when I wrote down the multiplication form or the L infinity functional calculus, there was this assertion that if f n converges to f pointwise and bounded, then the corresponding operators also converge. Okay. So, that is an easy corollary, right, because you are simply multiplying by your function. So, if f n, so let me write one line. So, f n converges to f in pointwise and bounded, then you are looking at multiplication by f n, right, that is your operator. I want to know if that converges to multiplication by f in the strong operator topology, right. So, what do? You acted on some function. So, m f n at g, whether does this converge to m f at g, right. but what is MFN at G? That is multiplication by G, multiplication by Fn, and question is that converges to multiplication by G in the Hilbert space, but that is just DCT, right. Fn converges to F pointwise and bounded. G is in L2, all Fn's are bounded by some fixed constant. So, DCT will tell me that this happens, right. So, this happens by DCT. So, that is all is there in the pointwise and bounded thing. And it is a continuous star homomorphism is also trivial, because the norm of if phi is bounded, the definition is phi of A is multiplication by phi of x, right. So, the norm of phi of A, so this immediately implies that norm of phi of A is less than or equal to the supremum, right. So, that is the L infinity norm of phi, right, on the set minus norm A to norm. Okay. So, what remains is to prove L infinity functional calculus implies resolution of identity. Okay. So, that is what we will do in the next lecture, but this also part of it you have already seen. So, if you remember the initial proofs where we did spectral theorem in terms of projection valued measure, and then defined L infinity functional calculus or projection valued measure independently and so on. We saw how to go from one to the other, right. So, from L infinity functional calculus you can go to projection valued measures and vice versa. So, once you have the projection valued measure, it is easy to define the resolution of identity. Remember, we are in the self adjoint case. So, the spectrum is contained in the real line. So, we can simply take the set minus infinity to T and look at the corresponding projection which comes from the projection valued measure, which is simply the L infinity functional calculus, right. So, that is what we will do in the next class. So, we will stop now.